Good morning, boys and girls, and welcome back. Today we are going to talk about parametrics. We're going to do a quick little review from trig pre-calc days and introduce parametrics from a calculus point of view. All right. So, real quicker, let's talk about a quick function here. If we're talking about a ball being kicked or like a bomb being shot off, something like that. As illustrated in this graph here, generally we use like the x and y axis, x standing for the horizontal distance and y standing for the vertical distance that the ball has gone, right? Or sometimes what we might do is we might talk about the time the ball is in the air versus how far it goes and the height, or the time and the distance. But we kind of get caught here because if we start talking about time, we don't have room for three variables. And so this is where parametrics comes in, is we can talk about the path of this ball with the horizontal distance x, in terms of t, and the vertical distance y in terms of t. And so when we start doing this, we split up and we use two different equations for the horizontal and the vertical, and we're talking about this in terms of time. This is what you call a parametric equation. All right, and sorry my notes are coming up a little bit light here, but you should have your own that you can print out if you have not already. You're going to want to print these off, and you can use them or make sure you have a copy from me. But again, a parametric equation is going to be in the form of x equals f of t and y equals g of t, or some other variable besides t, but generally we're talking about the time the stuff is in the air. All right, so now if we want to find the slope of that parametric curve, or the derivative dy dx, what you're going to find is dy dt over dx dt. And when you divide those, you end up with dy dx. Okay? So these are some formulas you're just going to want to memorize and know. And again, just so long as dx dt does not equal 0. All right? But that's how you find the derivative or the slope of a parametric curve. The second derivative is the first derivative, dy dx, taken with respect to x, the second derivative taken with respect to x. And so the way we do this parametrically is you are going to take the derivative of dy dx with respect to t, and then you're going to divide that by dx dt. Okay, so take the derivative of dy dt with respect to t, and then divide by dx dt. And you will see some examples of this down below here in a second. The velocity of our object is given by the vector, and again, remember with vectors we use the, like little greater than less than signs, kind of ish. But the vector x prime comma y prime in terms of t. The acceleration vector is x double prime comma y double prime. So it kind of makes sense tying in with our velocity and acceleration that we've talked about before. Velocity is the first derivative, acceleration is the second derivative. You just put that in a vector. The speed of the particle is given by this equation right here, the square root of f prime squared plus g prime squared. Okay, and again, f was the x term and g was the y equation. Okay, so x prime of t, you could also say, or y prime of t squared. And the arc length of a parametric curve is the integral a to b of f prime of t squared plus g prime of t squared. So these are some formulas we're just going to want to know, be familiar of. I would highly suggest you put these in your calculator. Parametric and polar stuff are frequent calculator questions. So these are ones I would say that probably are worth your time to plug into your calculator, all these equations here. Once you know them, though, the stuff is actually not too bad, and it's just a lot of plug-in equations. So here's our first example. Given x equals the square root of t and y equals 3t minus 1, we want to find the slope and concavity at t equals 1. So, slope, again, is equal to dy dx, right? And the way we said we're going to find dy dx is y prime over x prime. Take the derivative of y with respect to t and take the derivative of x with respect to t. So in this case, I would get 3 over 1/2 t to the negative 1/2. And if I simplify that, that would simplify to, if I flip and multiply, I get 6 root t. All right, see? Nice and easy. That's the slope. Now we got to find the concavity. Concavity comes from the second derivative. Hold up one second there. I got so excited, I forgot we got to find the slope at t equals 1. So when I do it at t equals 1, I plug in 1 to the derivative and I get 6 root 1 or 6. So the slope at t equals 1 is 6. Now let's go find the concavity from the second derivative. So again, to find the second derivative, what we're going to do is we're going to take the derivative of the first derivative with respect to t, and then divide that by dx dt. So this would give me 3t to the negative 1/2 over, again, dx dt was 1/2 t to the negative 1/2. And when I simplify that, the t's kill off, and I'm going to end up with just 6. So because this is positive, I know that my graph is concave up. And again, because there's no place to plug in a t, it's going to be concave up everywhere. All right, let's move on to our next example, number 2. We're given x equals t cubed and y equals 3t plus 1. And we want to write the equation for the tangent line when t equals 2. So again, remember, when you want to write the equation of the tangent line, you need a point and slope. So let's go find these things. We need a point and slope. To find the point, again, the point is x, y, right? So we got to go find our x and y coordinate. So x equals 2 cubed, because x equals t cubed, or x is going to equal 8. And y equals 3 times 2 plus 1, or y is going to equal 7. So there's our point. Nice and easy, 8 comma 7. Now we just need to find the slope. To find the slope, again, we just got to do y prime over x prime. And in this case, that's going to give us 3 over 3t squared. And when I simplify that, I get 1 over t squared. And when we evaluate that at t equals 2, we end up with 1/4. 1/4. So now we got our point and slope. So now we just got to write our equation. Y minus 7 equals 1/4 x minus 8. I have a feeling you guys are going to like this a little bit better than our unit on series. I don't know. Once you memorize, again, once you know these formulas, it really is not too bad. All right, next one here. Given our parametric function x equals t squared minus t plus 2 and y equals t cubed minus 3t, we want to find the points of horizontal and vertical tangency. All right? So if we're looking for horizontal and vertical tangency, that's where the slope is going to equal 0 or is undefined. We know that a horizontal tangent would have 0 slope, and then we know the vertical tangent, the slope would be undefined. So now we got to go find our derivative. And maybe that's not 100% true, because I know, again, dy dx is y prime over x prime, and we know that dy dx is going to equal 0 when the top, or y prime, is equal to 0. So I'm just going to go ahead and find y prime, which is 3t squared minus 3, and I'm going to set that equal to 0 and solve. And that is going to happen at t equals plus or minus 1. All right? Now, remember, the directions said to find the points of horizontal tangency. So we need to actually go back and find our x and y coordinates. So when we plug 1 into x and y for the first point, when I plug 1 in x, I get 2. And when I plug 1 into y, I get negative 2. Now I got to go plug in negative 1. And when we plug in negative 1, we get 4 and 2. So the 2 points for the horizontal tangent are 2, negative 2, and 4, 2. All right, there we go. Now we got to go find the vertical tangents, right? So this is where the derivative is going to be undefined, or where the bottom equals 0, x prime equals 0. And so x prime is 2t minus 1, and that equals 0 at t equals 1/2. Slide over a little bit so I got some room. All right, and so now I need to go and find, again, that point. Don't forget to read directions. We want the point of vertical tangency. And when we plug into our x and y equations, we're going to get 7/4 and negative 11/8. And so the point of vertical tangency would be 7/4 comma negative 11/8. All right, we're going to skip number 4 because it's just like this one here, and we're going to move on to number 5. All right, number 5 is asking us, given a particle whose position is defined by x equals cosine t and y equals sine 2t, find the particle's speed at t equals pi over 2. All right. So to find the particle's speed in a parametric situation, we are going to use the equation, the square root of x prime squared plus y prime squared. So x prime is negative sine t, and if I evaluate x prime at pi over 2, we get negative 1. And then I got to find y prime and evaluate it at pi over 2. Y prime is cosine 2t times 2, and when I evaluate that at pi over 2, we get negative 2. All right, so now that I know those values, we can plug those into our speed equation. So the speed of this particle, when I plug in x prime and y prime, evaluate their relative values, is the square root of 5. So just a lot of plugging and chugging in formulas. Not so bad. All right, number 6. All right, for number 6 here, we're given that x equals t squared plus 1 and y equals 4t cubed plus 3. And and we want to find the length of the curve on the interval from -1 to 0. So again, arc length is the integral a to b of the square root of x prime squared plus y prime squared dt. So now I'm going to go find those two things. So in this case, we're doing the integral from -1 to 0, because that was our interval. Square root of x prime is 2t, quantity squared, plus y prime is 12t squared, dt. And now I can simplify that a little bit, and we get, and I guess I didn't have to do that because this is a calculator question, most definitely. You are not going to integrate this by hand. So plug that in your calculator, and you should end up with the arc length as 4.1493. All right, and number 7 again is just like number 6, so we are going to skip number 7. Okay, boys and girls, well that's pretty much parametrics in a nutshell right there. Let's see if we can't do an FRQ. All right, a particle is moving along a curve in the plane. It has position x of t, y of t, at time t equals t, where dx dt is given by that function, square root of t to the 4th plus 9, and dy dt is given by 2 e to the t plus 5 e to the negative t, for all real values of t. At time t equals 0, the particle is at the point 4, 1. We want to find the speed of the particle and its acceleration vector at time t equals 0. So speed again is going to be the square root of x prime of 0 squared plus y prime of 0 squared. If we plug 0 into dx dt, I get 3. And if I plug 0 into dy dt, I'm going to get 7. So I'm going to take the square root of 3 squared and 7 squared. And we get the speed is the square root of 58. The acceleration vector, again, acceleration is the second derivative. So it's x double prime is 0, y double prime is 0. X double prime is 1/2 times 2 to the 4th plus 9 to the negative 1/2 times 4t cubed, chain rule. Now I got to evaluate that at 0. And when we plug in 0, I get a bunch of stuff here times 0. So there's just going to be 0. Next, I got to find y double prime. And so y double prime is 2e to the t plus 5e to the negative t times -1. And then when I evaluate that at 0, e to the 0 is 1 and e to the negative 0 is 1. So I get 2 minus 5, which is -3. So our acceleration vector would be 0, -3. So there are two answers right there. All right, perfect. Moving on to the next part. All right, part B says define an equation of the line tangent to the path of the particle at time t equals 0. So we need the slope at 0 and a point. So the slope of a parametric equation would be y prime is 0 over x prime is 0. And we found those in part A, and that would be 7/3. The point they actually give us in the beginning of the problem up here, and sometimes these can be tricky if you forget about it, but they told us up here that the point is 4, 1. All right, so they gave us the point in the very beginning. But now we have the point and the slope, we can go ahead and write the equation of our tangent line. And as always, I would leave that in point-slope form, just like that. All right, next, boys and girls, we want to find the total distance traveled by the particle over the time 0 to 3. So that would be equivalent to arc length. So arc length in this case would be the integral from 0 to 3 of x prime squared plus y prime squared dt. And they gave us x, y, and y prime, so we just got to plug them in. And I plug this into my calculator, and you're going to end up with 45.2268. All right, last part, part D. We now just need to find the x-coordinate of the position of the particle at time t equals 3. So to find the x-coordinate of the particle, we have the velocity or the derivative, so I think I'd have to integrate it. And if I'm looking for the position at time t equals 3, I'd want to integrate it from 0 to 3, since this would equal x sub 3 minus x sub 0 by use of the fundamental theorem of calculus. So now I can solve for x sub 3. And x sub 3 would equal x sub 0 plus the integral 0 to 3 x prime of t dt. Or my starting position, and that's the change in the x over the time. I know the starting position was at 4, and then I can integrate the derivative, and we get that our final position at time t equals 3 is 17.9307 when I use my calculator. All right, boys and girls, that is parametrics in a nutshell. Hope you enjoy it as much as I do. If you got questions, come find me. Otherwise, see you later and have a nice day.